And there's some information from other galaxies. All three of these, in fact, have been mentioned during the course of the meeting by the people that were involved in their observations. And in each case, there's an indication, so not through the type of modelling that I've been talking about here, but in each case, for separate reasons, there's an indication that there's basically an axially symmetric mode to the large-scale magnetic field that describes the field structure. So to try and summarise this for the 5 cases that I showed, in each of these 5 galaxies, these 5 disk galaxies, we find there's always this axially symmetric mode is required to describe the large-scale magnetic field. In one case, in the case of Andromeda M31, that's all that we need. That's the only mode of the Fourier series that we need. In other cases of normal spiral galaxies, we need some higher modes, or a vertical field, in this case, or a vertical field stroke, something to describe the warping of the disk of that galaxy. In the case of M51, we have a low amplitude MS2 mode. The numbers here are referring to the relative strength, so the strength of these higher modes relative to the axially symmetric mode. So basically, the axially symmetric mode is the strongest, or the equally strongest mode. It's required to describe the large-scale field in all of these galaxies. And so, what I would propose is, what's interesting now is, what's the simplest type of dynamo model that you would need to describe the fields that are observed in disk galaxies? And I think you need something that's basically going to give you this mode, this axially symmetric field configuration, in any type of galaxy, in a generic spiral galaxy, whether it has a strongly distorted velocity field like a barred galaxy, or a rather simple velocity field like this case, or a very strong 2-arm spiral pattern with associated streaming motions, which are radial in and out motions, like this case M51. What we're seeing always now, it seems, is this axially symmetric mode is required to describe the large-scale field. And the other thing that we find is we can make a measurement now, an accurate quantification of the pitch angle of this M0 mode. So the pitch angle is just the ratio, the tangent of the pitch angle is the ratio of the radial component of the field to the azimuthal component of the field. We cover both the radial and azimuthal components through this fitting process, so I can calculate the pitch angle of this M0 mode. And that's what's shown here. So we have quite small pitch angles in the case of Andromeda, going to quite very large pitch angles in the case of M33. So the interesting thing is that none of these pitch angles are very tiny. So the galaxies are rotating with lots of shear in them. And you can imagine just winding up some ambient field, winding it up more and more times, stretching it out and shearing it. Eventually that would give you a pitch angle of the field that was very, very small, a tiny pitch angle. What we find is that you always have a non-zero, non-trivial pitch angle. There's always some amplitude of the pitch angle here. It's quite well defined. In this case, say, this minus 10 degrees. This is minus 10 degrees plus minus 2 or 3 degrees. There's no way it's near to 0. We can do something a bit more with the pitch angles. So we can compare the pitch angles with what you expect from the simplest version of the mean field dynamo theory. So I'm hoping that Anwar agrees with this equation for the pitch angle. What we have is the ratio of some component of the dynamo number that's to do with the alpha effect that produces radial field to the component of the dynamo number that's to do with the differential rotation that produces the azimuthal field. So you've got radial field over azimuthal field with some prefactor. So we can if I make an estimate for what the magnitude of the alpha effect is, and I've assumed I've just taken 1 kilometre per second because I know no more about that for these particular galaxies. But I can know what the rotational velocities of these galaxies are, so I can estimate what the shear is at different radii. And make an estimate of what the scale height of the gas layer is, either from observations or by some scaling with what I know about the Milky Way or typical disk galaxies. Then I compare the pitch angles that I measure, which are these red points with error bars, with the pitch angles that are expected from this equation and some observed or estimated parameters of the different galaxies, which is shown by the blue line. And so for these two cases, M31 and M51, I get not a bad match. So for M31, the pitch angles match to within, say, up to 10 degrees. And this is for the absolutely simplest dynamo model you can have. You write the equations down on the back of an envelope, and then take this ratio. So in the case of M51, I've got an offset of about 5 degrees consistently at all radii, so I'm showing radius along here. In the case of M33, I've observed, measured very strong, very high pitch angles of about 40 degrees. This very simple model is out by about 20 degrees. So things are not working so well there. But this very, just to emphasize again, this is a very simple dynamo model that is being compared there.
You
so,
need to assume something about the turbulence scale or something, right?
Yeah. So all of that is just wrapped up in what I've taken for my alpha. I've just out of the thin air said, okay, the turbulent velocity is something like 10 kilometers per second, and I'll take my alpha to be about 1 kilometer per second.
So if you increase that, you will.
If you increase this alpha, then you would reduce the pitch angles, and so if you increase this alpha, you would shift this blue line down. But you'd want some reason to do that for that particular case. Yeah.
But you have no reason for 1 kilometer per second either.
No, I don't. No. I have the same 1 kilometer per second in all three of these, though. Okay, so now my time's going. So I'll just, if we look in some detail to what happens with the pitch angle of the magnetic field, as I go around in a circle, so I pick some constant radius and follow the pitch angle of the field as I go around in a circle. You see I pass through two of these spiral arms, these bright spiral arms, one here and say one here. And what happens to the magnetic field when we do that, if we look at some detail? So here's my two spiral arms, these red lines. This is the artist's impression of what's going on, rather than the data. So these blue lines are the magnetic field. And the magnetic field, the regular magnetic field, can be quite misaligned. Its pitch angle can be quite different to the spiral arms, away from them. And when it passes through the spiral arm, it becomes very well aligned. And then its pitch angle moves away, its orientation changes, then it gets well aligned again. And I think this is the origin of this M is 2 mode in a galaxy particularly like this. And we don't necessarily need to look for some kind of dynamo explanation for why we have an M is 2 mode. Basically, the field gets lined up when it gets to the spiral arms through some kind of compressive shock or shearing effect, and away from the arms it drifts. And my time is gone, so I'll go back to one final thing, the magnetic arms. Here's the galaxy M51 again, and these various coloured lines show a trace of where the ridge of the spiral arms are and all various traces. The interesting thing here is this blue line, which shows the ridge of the regular magnetic field, the large-scale magnetic field. And you can see it's wandered away from the other traces of the spiral arms. So it wanders into the interarm region here. There's quite a big pitch angle. It crosses over the spiral arm and goes on to the next spiral arm. The interesting thing is some people have recently taken a high-resolution velocity field for this particular galaxy, and they've been able to measure very strong non-circular motions. They've been able to measure radial velocities, so that's velocities in these directions that are up to between 50 and 100 kilometers per second. And that's to be compared to the circular velocity, like this, that's about 200 kilometers per second. And this wandering ridge here, this interarm region, this magnetic arm, happens to line up and follow some peaks here of this radial velocity. So when we have this set of peaks of radial velocity, of strong radial velocity, up to about 100 kilometers per second, over a region here of about 4 kiloparsecs, these peaks just happen to line up with the location of this strong interarm magnetic field, so this kind of strong wandering magnetic arm. This is something that, this level of resolution of velocity field I've not been aware of before for any other galactic system. And I just came across this coincidence, which is all I would say is when I was preparing this talk last week. But to me, somehow this is telling us something, because the pitch angle of this magnetic arm here is greater than the pitch angle of the rest of the spiral pattern. And so if you imagine you have a strong radial velocity, it's a velocity in this direction, that radial velocity will naturally try to make you a higher pitch angle. It will naturally try and shift the pitch angle of this structure outwards. So I'm wondering whether this kind of strong ridge of high radial velocities can be an explanation for these wandering magnetic arms that we see. I'll finish there. Sorry, Dimitri.
Thank you very much. Please, questions.
Question about what you said about these radial velocities. Velocities. What you really observe is the line of sight velocity. So you need some estimate of the velocity in the plane of the star.
Yeah.
Before you infer anything about.
Yeah.
How do they do that?
How do they do that? What they do is, so if I show you what this figure on the right is their velocity field, which is very high resolution. What they do is they take they say, okay, these white lines, they're the lines of their spiral arms, that they fit it sort of this structure and this structure. And they say, okay, now I'll make a whole set of these spirals, and they deproject this galaxy according to an inclination that they estimate due to the large-scale structure of this velocity field. And then they look at deviations from circular velocity at a fixed phase along this spiral. So what they do is they shift this map into a map of spiral phase. Probably not explain that, but if you imagine a whole set of these logarithmic spirals, and then you pick a position at a certain radius, and you go from one bit of spiral to the next, to the next, to the next, to the next, eventually end up at the next spiral arm. And so what they do to get this velocity field, this coordinate here is the phase in spiral structure. So these are different radii, a low radius and a high radius. And then these blobs here are how I've marked where the spiral arms are. So this is a shift in spiral phase. You're right that it's not such a trivial thing to do. But this is quite an involved set of modelling that they've done, and there are all kinds of tests with, assuming we have a different inclination, how sure is our result, and so on. And so the thickness of this line here is their estimate of the level of certainty or the error in the radial velocity. So this column is radial velocity, this is azimuthal velocity. So they're also their estimates of the uncertainties in this. I can't explain any better off the top of my head.
Fine. I have a related question. Can I ask? In the other galaxies where you were comparing things with dynamo models,
Yeah.
wouldn't you need again information about the total velocity field in the galaxy?
Yeah.
Before you can.
I did that. So sorry. I mean, I thought. So I would take what I took was an estimate of the large-scale shear, of the shear
Based on
the rotation curve, based on the observed rotation curve. I'm sorry if I didn't make that
So
clear.
that assumes that most of the motion is circular.
Absolutely, yeah, absolutely.
What happens with the bar galaxy, where you have streaming motions along the bar?
Well, to me, the concept of rotation curve isn't so useful for a bar galaxy, because you basically don't. So that's why I didn't make that comparison of the pitch angles for the bar galaxies, because I wouldn't be sure which velocities to
So you
take.
didn't fit that with the
No, I didn't try that. No.
More question, please.
Yeah, I mean, the m equal to 2, you can always explain by this compression, but m equal to 1 component anywhere, you probably need a dynamo type explanation, I think. And in that case,
Just some asymmetry, I think. Just some. I mean, what's especially for this type of system, this.
or just asymmetry between north and south, something like that. Is it okay?
Yeah, I mean, even this case, so this galaxy looks quite symmetric about rotation. It's not quite so straightforward. So there's usually some kind of large-scale asymmetry between north, south, east, west, or whatever, however you want to divide it.
That's enough to give you equal power in m equal to 0 and 1?
I couldn't say, but I would offer that as another speculative reason as against trying to find a dynamo reason.
But Andrew, when you go with 1 and 1, probably this means 1.2 and 0.8 rounded up. So they can easily be fucked with 50% difference in amplitude. Still, 1 and 1 means 0 on one side and 2 on the other. Of course it's not like that. It's just rounded up figures. Oh.
Yes, so I mean, can you produce equal m equal to 0 and m equal to 1 by asymmetry? I'm not sure.
Not really. This would be it.
And then you require the non-axis symmetric effects in the dynamo, which has been discussed for a long time. But we all forgotten about it because of other problems.
But the point is now that none of these systems show that you need this non-axis symmetric dominant case to describe.
M81, which Rainer.
But that system was analysed using not such a way of modelling. So it was analysed by basically looking at something and seeing whether it's got one period or two periods.
So you should probably look at that. Or
Yeah, the data are unsatisfactory, the data are unsuitable, so we've re-observed it.
oh.
And now we're going to apply the same modelling once those observations are available. And then you should get a definitive answer.
What question, please?
Yeah, you presented a table with magnetic pitch angle which differs from different galaxies. And what about the pitch angle of spiral arms in these cases? They are similar or not? So, in other words, they are magnetic pitch angles are modified by the spiral arms or are due to this formula of the dynamo action.
Here, in the case of M31 and M51, they're similar pitch angles of the spiral arms. In the case of M33, you don't really have well-defined spiral arms anyway. You have lots of fragments.
Roughly agrees.
They have quite a large opening angle, but you don't have something that traces the whole half system. No, well.
Oh, yeah.
Somebody's drawn some lines on a map with a pen, but it's...
No, it's not that bad. So I would agree with Christoph. They really agree well. So in the case of M33, there's really a problem with the standard estimate from dynamo model. So it doesn't work. It's a factor of 2 too small. We see 40, and 40 is nearer to what you see in H1 and the optical spiral arms. I think this is 99% safe statement.
Okay.
So, as I see, our time is finished. Let us say. The time, so the first talk 40 minutes and the second talk 20 minutes only. So let us start.
So those who are absent suffer. I mean the second one.
Oh.
Okay. Generation of large-scale magnetic field in a shear non-helical turbulence. This work has been done in collaboration with the Okay, outline of this talk. So we consider turbulence with imposed large-scale velocity shear. And we would like to discuss several effects related with the turbulence in the shear. The first is the effect of kinetic helicity fluctuations on mean field dynamo. In order to study these effects, we use Tau approach and second-order correlation approximation. Then shear current effect, we use also Tau approach, SOCA. SOCA is first-order smoothing, just the people use this to name. And also the renormalization procedure. Also there is a related problem, so-called vorticity dynamo, generation of large-scale vorticity in shear turbulence. And we will discuss applications and laboratory experiments. So main question is, which we would like to discuss, is it possible to generate large-scale magnetic field in a non-helical and non-rotating homogeneous turbulence? Non-helical means that turbulence with a zero mean kinetic helicity. So classical mechanism of generation of large-scale magnetic field is related with the alpha effect and kinetic helicity. Just several words about the mechanism of alpha effect, because we will use some analogy at some moment. So if we have turbulence which is inhomogeneous with uniform rotation, then alpha effect is caused by dynamic helicity or kinetic helicity, and original deformation of original magnetic field is caused by the upward and downward turbulent eddies. And since turbulence is inhomogeneous, the effect of deformation caused by the upward eddies is not compensated by the deformation caused by the downward eddies, and it can result in generation of large-scale magnetic field. But do we really need kinetic helicity for generation of large-scale magnetic field? Let's consider the first problem. Mike Proctor told about this problem, so it's easy for me now. So we consider kinetic helicity fluctuations with zero mean value. In the first problem, which was posed by Bob Crichton in 1967. Unfortunately, 3 weeks ago, Bob Crichton was died. He's the greatest American scientist, which his contribution to turbulence theory, to the transport of passive scalar magnetic field is very important. Okay, so what is the problem? So we have a forcing which produces small-scale turbulence from the scale of, from viscous scale to some scale L0. Then there is another forcing which produces kinetic helicity fluctuations in scale from L0 to L car. And mean field effects implies that we consider scales which are much larger than the L car scale. In principle, this problem has been considered in a number of people. Different aspects of this problem discussed in these papers. Our motivation was has been strongly motivated strongly by the paper by Mike Proctor. And okay, so we studied this effect using tau approach and the first order correlation approximation, the second order correlation approximation, or first order smooth. Of course, the first effect which we reproduce by both methods is the effect found by Bob Crichton, which means that kinetic helicity fluctuations causes negative contribution to turbulent magnetic diffusion. Here, tau chi is a time which is the ratio L chi squared divided by the sum of turbulent diffusion and magnetic diffusion caused by the electrical conductivity. Okay, the second effect which we covered is the appearance of large-scale drift velocity. If there are inhomogeneous kinetic helicity fluctuations, then there is a drift of large-scale magnetic field to the regions with the higher fluctuations of kinetic helicity. And this effect, I think, in the first was found by Keith Morgan. Okay, the third effect is, okay, these two effects occurs in a shear-free turbulence. You have a turbulence with imposed large-scale velocity shear, then combination of large-scale shear and homogeneous kinetic helicity fluctuations produces mean alpha effect. In spite of the mean value of fluctuations of y equals 0, nevertheless, mean alpha effect is not 0. And if we consider shear flow, for example, simple shear flow, there is velocity in y direction and homogeneous in x direction. So there is a large-scale vorticity which is in the z direction. So alpha effect is caused by these derivatives of the alpha square fluctuations. And this effect in the first was discussed, and of course in combination with the shear flow, this effect causes large-scale diamond. The first this effect was discussed by Silankov in 2000, but I agree with Mike that his paper is it's difficult to extract even this result from this paper. Okay, and the next, the fourth effect. So if we have homogeneous kinetic helicity fluctuations, so in this situation, these two effects vanishes, and there is, of course, negative contribution to turbulent magnetic diffusion. And what about the effect of homogeneous kinetic elastic fluctuation to the mean field dynamo. What we found using two approaches that there is a negative contribution to the mean field dynamo. So if there is some mechanism which can generate magnetic field, then these kinetic elastic fluctuations homogeneous causes decrease of the growth rate. And this result in disagreement with the result by Mike. And in principle, this result can be obtained using by Soka using several minutes. Maybe in the discussion I will propose this result by Soka. Okay, now let us continue. But do we really need kinetic elasticity or kinetic elastic fluctuations in order to generate large-scale magnetic field in homogeneous turbulent flow? The answer, we don't need. First simulations. The first simulation has been done by Axel in 2005. It's published in 2 papers. He considered non-helical, constant in time, sinusoidal forcing, which causes imposed nonlinear mean velocity shift, open boundary conditions, and there is exponential growth of the large-scale magnetic field and then saturation at the level of equipartition. Simulations by Dmitry Shapovalov and Vishniak are very similar to these simulations. Okay, the next simulation has been done recently by Tarek Youssef and Thomas Kuhneman, also Alex Chikachikhin, and we take part in this this work. It was used a code written by Skakov. I will speak about these simulations in the second talk. Just here I would like to stress that here there is a forcing of turbulence, white noise, non-helical, homogeneous, and basotropic random forcing, and shearing box. So there is imposed mean linear velocity shear in the system, and Franklin number is observed of unity, so there are no small-scale dynamo, but nevertheless there is exponential growth of large-scale magnetic field. Okay, we'll discuss the simulations and compare with the theory in the second part of this talk. Let's discuss the theory. So, okay, so in the frame of mean field approach, when there is mechanical turbulence, so mean alpha effect is 0, alpha B term in the mean electromotive force vanishes, but if we impose to the system large-scale velocity shear, then there is at non-zero background vorticity. An additional term in the mean electromotive force arises. This is vector product of background vorticity multiplied by the J. How it's possible to understand, first of all, the physics? Let's compare this effect, WJ term, with the alpha B term, called by the kinetic elasticity and alpha effect. If we have rotation, uniform rotation and inhomogeneous turbulence, then alpha effect is determined by this scalar product multiplied by the maximum scale of fluid motions. If we consider WJ term of shear current effect, we can rewrite this term in the following form. Just J the kernel of B, and one term is scalar product vorticity by lambda B, where lambda B is non-uniform mean magnetic field. And there is also the term with a gradient, but it doesn't depend because in the equation, in the mean field equation, curl of this electromotive of this term equals 0. Okay, so if we compare these two terms, we see that here vorticity plays a role of uniform rotation, and lambda B, homogeneity of the original mean magnetic field, plays a role of inhomogeneity of turbulence. and it can cause large-scale dynamo. How this effect works? So if we have deformation of original magnetic field lines is caused by the upward and downward turbulent eddies, since original magnetic field is non-uniform, so it breaks the symmetry between the action of upward and downward turbulent eddies, so it can, its total effect of deformation is non-zero, it can produce electric current along the mean magnetic field. So how this effect works? So if we have shear flow, of course, the trivial effect, if we have shear flow in y direction, homogeneous in x direction, so the x component of magnetic field is stretched, which causes generation of the y component, but it is not yet a dynamo, so we have to close a loop. And the shear current effect interaction of the background vorticity with non-uniform magnetic field By produces electric current along the original magnetic field, which applies generation Bx component from By component, and it can cause to dynamo. And in the language of equations, let's consider a very simple setup. So velocity in y direction, so background vorticity in z direction. So the first equation for the y component is the following. So shear, this shear stretching of the dx component produces the y component. This is turbulent magnetic diffusion. And this effect of interaction, due to the interaction of shear, vorticity, S multiplied by L square maximum scale of fluid motion, and multiplied by the second derivative of the y component. So this is here we consider a very simple setup. So magnetic field is depends only on z, and so from here we see that the growth rate of the large scale magnetic field is the following form. So the main question: what is the sigma b? If sigma b is positive, there is a dynamo. There is scale, there is a dynamo. And if it is negative, there is no dynamo. Okay, we studied this effect using different procedures. Tau approximation. Also, this effect was studied by using second order correlation approximation. Recently, we applied another procedure, the renormalization procedure, in order to study this effect. The result is following. Of course, the main contribution to the effect from the maximum scale fluid motion. But the result depends on the scaling of the relaxation time, correlation time on K. So, for example, if we have large Reynolds number and magnetic Reynolds number, so if scaling is Kolmogorov scaling, then in this situation, this coefficient sigma b is positive. And also, if we have small scale dynamo, it causes positive contribution to the shear current effect. And even in convection, if we have convection, then convection heat flux causes positive contribution to this effect. Now, but if we consider small Reynolds number and small magnetic Reynolds number, where the scaling of the correlation time just like viscous scale or diffusive scale, so this correlation time depends like a k to the minus 2. In this situation, there is no dynamo due to the shear current effect. In the presence, if there are no magnetic small scale dynamo and no convection. And in principle, this result is in agreement with the SOCO result, studied independently by Karl-Heinz Redler and Stepanov and Rudger and Kitchetin. So results depends on the correlation time. So let's consider large Reynolds number, but arbitrary magnetic Reynolds number. So the inverse correlation time is a combination of inverse diffusive time and inverse turbulent time. In this situation, threshold for excitation of large-scale magnetic field is of the order of 10. But if we consider not small Reynolds number, not small magnetic Reynolds number. In this situation, the threshold for excitation of large-scale magnetic field is Reynolds should be more than 1, 2, 3, okay, but so threshold is not so high. Maybe this is the reason why in numerical simulations, even for not high Reynolds number, generation of large-scale magnetic field is observed. In the second part of our talk, in the numerical simulation, I will show the requirements for when there is a generation, where there can be generation of large-scale magnetic field due to the shear current effect. Okay, now, if we consider very simple Kraikin-Kazantsev model of turbulent velocity field, delta correlated in time velocity field, most simple model. In this situation, of course, there are no effect, because effect of shear implies small but finite correlation time. So this is the reason, of course, that in delta correlating time random velocity field we cannot obtain the effect of generation of large-scale magnetic field. So, if we have both kinetic helicity fluctuations and shear current effect, so if we have a shear which is superimposed on turbulence, so shear current effect should be exist. Of course, it can be, this coefficient can be negative, so which cannot produce dyne. But what we found that kinetic helicity fluctuations decreases the growth rate of the large-scale magnetic field. And this was found by two approaches, and I'm sure that the normalization procedure also yields the same result. Now, let's study this dynamo. So let us rewrite these simple equations. So B depends on Z in dimensionless form, so measuring time in the turbulent diffusive time. Then there is one parameter on the system, dynamo number, which is the ratio of maximum scale of motions to characteristic scale of shear multiplied by the non-dimensional shear number. And this parameter, dynamo number, should be more than 2. And of course, theory is valid when shear is not large. So, in the case of when shear is not large in comparison with the correlation time. So, theory implies that shear S multiplied by the correlation time is smaller than u. Okay? So in this situation, theory can be developed. Okay? There is a related effect. Since induction equation is very similar to the equation for the evolution of vorticity, then we can expect that vorticity, large-scale vorticity, can be generated in a shear turbulence. Of course, there is a difference because vorticity is a curve of velocity, and velocity is determined by the nonlinear Navier-Stokes equation. But there is similarity. Uses the same setup. So we have a large-scale shear velocity, which depends, which is in y direction and depends on x. So the ground vorticity in z direction. We derived equations for the evolution of perturbations of vorticity. And for this simple problem, where magnetic field depends only on z, the equations for the evolution of vorticity are very similar to equations for evolution of magnetic field. They are not the same because Wx component, equation for the Wx component is similar to equation for By component, and equation for y component of perturbations of vorticity is similar to equation for the little Bx. So it yields that the growth rate has a similar form. Of course, the physics is very different from the physics of generation of magnetic field, but this similarity between these equations exists only in the case, in the simple case when magnetic field depends on Z. This corresponds to the maximum growth rate. But if vorticity depends on 2 or 3 special variables, equations of course are different. And physics of generation of vorticity is the following. Of course, we have stretching effect due to the shear. So stretching produces Wx component of vorticity from Wy component. And then effect of shear on Reynolds stresses causes Reynolds stress induced generation of large scale vorticity. And so Wy component is generated from the Wx. In principle, this mechanism is known from is related with the so-called frontal secondary flows. First mechanism is caused by the stretching, and the second mechanism of the frontal secondary flow are related with the Reynolds stress-induced generation of large-scale vorticity. But there is a similarity between these equations and the magnetic dynamic equation. Okay, now, since this kind of dynamo exists, it's interesting to study nonlinear evolutions caused by this dynamo, by shear current effect. So we study nonlinear shear current effect, and its behavior is different from the, for example, behavior of Wolff effect. There are no quenching of this effect, of this nonlinear shear current effect. There is only the change of the sign of this effect when the field of the order of equipartition field. So if we forget about the evolution of dynamic helicity, so maybe this region determines the saturation of the magnetic field and the saturation of the growth of the magnetic field. And numerical solution of nonlinear dynamic equation shows that there is saturation of the magnetic field caused by the nonlinear alpha effect at the level of equipartition field. But of course, most important non-linearity is related with the dynamics of magnetic helicity, and because even for very small large-scale magnetic field, magnetic helicity is not small, and it causes the dynamics. Okay, it changes strongly dynamics, nonlinear dynamics of magnetic field. If we take into account into consideration of dynamics of magnetic helicity, then of course everything depends strongly on the flux of magnetic helicity. Here we use very simple flux of magnetic helicity, like a diffusion, turbulent diffusion of magnetic helicity. And the numerical solutions of this equation show that if fluxes of magnetic helicity is very small, then saturated level of magnetic field is very small. But if we increase the flux of magnetic helicity, we obtain the saturated level of the equipartition field. I have mentioned that that during generation of large-scale magnetic field, there is a strong growth of By component, the component which is directed along the impulse shear, and this is very, so Bx component much smaller than By component, which is similar to alpha omega dynamo. But if shear is tau not of the order of unity, so these components are the same order of magnitude. Of course, if really this mechanism exists. So, and shear is very universal feature in astrophysics, which exists in many objects. So this mechanism can be important in astrophysics. For example, in protostellar clouds, protogalactic clouds, also for accretion disks, for irregular galaxies, this mechanism can be important. And application of this theory to the protostellar clouds and protogalactic clouds show that the level of saturation of the magnetic field of the order of equipartition, and this estimates yields reasonable numbers for these objects. And this effect has been studied, different aspects of this effect can be studied in the following papers, and these simulations will be discussed in the second talk. So, conclusions. Generation of large-scale magnetic field in a turbulence with large-scale shear is possible due to the shear current effect, which is caused mainly by the term vorticity cross B, cross J term in the mean electromotive force. And this mechanism can act even in non-rotating and non-helical homogeneous turbulence. Requirement for this shear current dynamo, Reynolds number and magnetic Reynolds number should be larger than 1, but it doesn't necessarily to have a very long range, inertial range in order to produce such kind of dynamo. Non-linear evolution of this effect is that there are no quenching of this effect, just there is a change of the sign of this effect. And magnetic helicity has, transport of magnetic helicity plays a very crucial role. And if flux of magnetic helicity is small, then saturated level is very small, but if flux is not small, magnetic helicity saturated level of the order of equipartition field. In the problem of with homogeneous kinetic helicity fluctuations, we haven't found the dynamo effect, and there are a lot of applications of this effect in astrophysics and in laboratory dynamo experiments, where, for example, in French dynamo experiment, BKS experiment, there is a strong shear. And the shear current effect can play a crucial role in this experiment. Also in paired dynamo experiment, there is a strong shear, which maybe this mechanism is responsible for generation of large-scale magnetic field. Okay, thank you very much for your attention.
May make some ask you about a obscure problem concerning the dynamo with fluctuations of helicity of alpha effect. The point is that if you are writing down the mean field equation, you consider V, which is average value of H, average of turbulent pulsations. If you and then alpha is average of V, root V and something down. If you say that this quantity has fluctuations, you anticipate that you have another ensemble of fluctuations, and then you have a choice. What are you interested in? Behavior of this B, or say this B in Gothic style, which is average of H plus another average of this another ensemble of fluctuation. It is a question which have to be somehow formulated answer before we can give more or less focused answer on this question. And can you somehow comment what is
Okay.
your statement of problem?
Yeah, okay. Of course, we have two independent forces. One produces small scale. Just a moment, Okay, so we have two forcings. One at small scales which produce velocity fluctuations, and there is another forcing which is in larger scales which produce kinetic velocity fluctuations and fluctuations of alpha. This is two independent ensembles. And so we have performed all derivations which relate to this problem imply that we have to have, we perform double averaging. First of all, we average over the ensemble of turbulent velocity field and obtain mean field equation. Okay? Like this. Okay, and plus, okay, so this is shear root effect, BW. This is the curl of alpha function B. This is diffusion, eta T and eta. Eta molecular diffusion, this is turbulent diffusion, and this is nonlinear terms. And then we have to, this averaging is performed, for example, in scales from viscous scale to some scale naught. Then, since alpha, the draft fluctuations of alpha, we have to perform next the second averaging, and in order to derive mean field equations. So of course we have double averaging, and of course there are some mathematical problems related with this the problem which study effects of kinetic velocity fluctuations. Some mathematical aspects of this problem have been studied in your paper in 1997. But of course, it's not so easy to realize this situation. Maybe in numerical simulation it's possible when you have two forces which are separated in scales. But how it's possible to find this problem in nature? Maybe we have some speculations that, just a moment, I'll finish in several seconds. We have some speculations, so we have symmetrical explosions of supernova, and while there is a small scale turbulence inside the convective zone of the stars, so there is some separation of scales and two independent forcings, but this is some kind of speculation, nothing else. Yeah?
Okay. Question related to just what you said.
Mm-hmm.
I understand velocity forcing on scales in turbulence.
Yeah.
You had written down another force string for kinetic helicity.
Yeah.
What is a likely physical source of forcing of kinetic helicity? Velocity forcing, I understand.
Yeah.
I can imagine.
Forcing of kinetic helicity doesn't exist, except in numerics.
In some sense, it's artificial, maybe. Problem. But from a mathematical point of view, it is a very interesting problem to study.
So maybe my suggestion is not to go just now into more mathematical details, because the topic looks obscure enough, and it is much more.
The purpose of the conference, Mitch, is to bring light.
Yes, yes.
There is only shadow now.
But you know, after the following talk, we have a discussion, and I would suggest, if moderator of discussion will agree, it is a great opportunity to make formulate your opinions and things like that. And now we have, I believe, moved to the following talk. I would like to say that the following talk is a great achievement on the way of political correctness. I would like to say that Igor represents in the following talk science of Egypt, and it is a great achievement.
Okay, the shear rate dynamo. So we'll speak about direct numerical simulations performed by Tarek Youssef, Toddy Kuhneman, also Alex Kachikin, and we participated from theoretical part of view. It was used, okay, at the beginning of simulations we used pencil code, and then we switched to the another spectral code written by Skakov, and also Steve Cowan and Mark Williams participated in this problem. Okay, so the same equation, do we need kinetic helicity in order to generate large-scale magnetic field? So there are successful simulations by Axel Brandenburg, and this is additional, okay, this is simulations which we discussed with where shear was introduced by non-mechanical constant in time sinusoidal forcing, and I think the simulation by Shapovalov and Khan-Vishniak are very similar, at least in the setup. The simulations which we would like to discuss, this is another setup. So we have white noise, non-helical, homogeneous and isotropic random forcing, produces background turbulence, and there is imposed linear velocity shear, both to the system. We use shear rate box, forcing, scale of forcing. Okay, it was used, I will explain why, in box with a large aspect ratio. So in LZ direction, LZ size of the box much larger than L8 and L1. Reynolds number is not so large. Okay, why we use box with a large aspect ratio? Okay, first of all, we would like to reproduce exactly the setup which used in the theory. First of all, we would like to consider small velocity shear. Okay? This is a growth rate. So gamma is positive when kz is less than this value, which implies that if we consider small shear, so the characteristic size of magnetic field variations should be more than U RMS divided by S. So if we consider small shear, LZ should be large. So simulation is setup of simulation is the following. So at a given shear, we take the size of the box in vertical direction. Vertical direction, this is just direction of change of magnetic field, just this set up, okay, the problem. So B depends on Z. So mean field implies that we average over X, Y plane. So, so it's very important that growth rate of the large scale instability occurs for, and if shear is small, so in this situation Lz should be large. So if double increase of the size of the box doesn't change the change of the growth rate, so we have convergent system. So this is a parameter range for the these numerical simulations. Unit size Lx and Ly is unity. So RMS is unity. So size of the box, size of the forcing scale 1/3. So correlation time 1/3. The growth rate is small, so we have to perform simulations in a very long time. And we see that so when we increase of size of the box, there is we will stop when the growth rate will be the same. Now next, okay, we observe generation of large-scale magnetic field. At this stage, we would like to study only kinematic stage. So, kinematic stage, we don't discuss here the saturation level of magnetic field. So, good news that we have relay generation with non-helical forcing. When we decrease Reynolds number, when we consider small Reynolds number and small magnetic Reynolds number, there is no generation. So there is agreement with some theoretical prediction to show that if Reynolds number is small, we cannot observe growth of the large-scale magnetic field. Also, we have, unfortunately, in these simulations, we have also generation of large-scale electricity. So in that sense, it's not so clear experiment. We see here two panels. This is RMS velocity, and this is growth of the large-scale magnetic field. And we don't observe here linear kinematic stage of growth of the vorticity, so it is saturated at some level. Okay. Now, of course, we cannot also introduce large shear. Okay.
Didn't you say it was kinematic?
Sorry?
Didn't you say it was kinematic?
We haven't observed kinematic stage of growth of vorticity in this system. Okay. But nevertheless, there is some nonlinear evolution of large-scale vorticity. Okay. Now, okay, field is concentrated. So here we don't have small-scale diameter. Okay, so we have only this is spectrum of magnetic field. So magnetic field is concentrated at the large scales. Of course, there is a tending. There is a tending of the large-scale magnetic field due to the presence of velocity fluctuations, but the level of these fluctuations is small. Very important that mode, very important for this simulation that mode that this scale is larger, scale of variation of magnetic field is larger than this value. This is very important. Maybe this is the reason why you don't observe generation of large-scale magnetic field. You don't have mode with them. Okay, wait. Okay, let's don't discuss with this. This is a suggestion.
Since you're about to say why I don't do something, maybe you'd like me to comment on it. Otherwise, don't fling out things like that during your talk.
Okay. Bad news. Okay. Theory predict this is a growth rate. It's easy to understand that according to theory, the maximum growth rate should be scaled as s squared. What we observe here is a linear scaling of the growth rate in the shear number. Okay? This is the first. Maybe we don't observe here modes with the maximum growth rate due to the complicated problem related with generation of large-scale vorticity. Maybe. The second, and correspondingly, according to the theory, the characteristic scale of magnetic field should be scaled for the mode with the maximum growth rate as 1 divided by s. Here we observe scaling s minus 1/2. Okay? Okay, thank you. Yeah. Of course, since we consider small shear, so this parameter is not large, so the y component is larger than the x component. And this is confirmed by numerical simulations. Similarly, if we consider vorticity, for the vorticity here, so here in this setup, by should be larger than bx. And here, vorticity, double perturbations vorticity should be larger than x component, should be larger than y component. This is what we observe in numerical simulations. Okay, when we included last rotation in the system, uniform rotation, then with a shear, then there is generation of large-scale magnetic field in this system, and there are no generation of vorticity. And we considered this problem, and we found that there are no generation of vorticity. Okay, so I think that very important purpose or goal of this program, at least for us, is understand the reasons why we have such scalings which are not consistent exactly with the scalings for the maximum grown modes, and consider this complex of problem related with the shear. Okay, thank you very much for your attention.
Thank you very much.